Good evening. My name is Sergio Verdu, and on behalf of the University Public Lectures Committee, I'd like to welcome everyone to tonight's Van Uxem lecture by Sir Roger Penrose, the second of a series of 3 lectures entitled Fashion, Faith and Fantasy in the New Physics of the Universe. It is, of course, impossible to do justice to Roger Penrose's scientific contributions in a brief introduction. He is the Emeritus Rose Bowl Professor of Mathematics at Oxford and the Pence Distinguished Professor of Physics at Pennsylvania State University. After graduating from University College London, Roger Penrose went to Cambridge, where, working towards his doctorate, he began to publish papers on semigroups and on rings on matrices. In 1955, he introduced a famous generalized matrix inverse, which has found numerous applications in linear algebra and in engineering. In 1957, he took his PhD in the field of algebraic geometry, and after a couple of academic positions in England, he came to Princeton in 1959 on a NATO fellowship, and then started publishing a series of important papers on cosmology. His fascinating work on non-periodic tilings also had its origins in the 1950s, and nowadays has found applications as diverse as recreational puzzles, non-stick coatings for pots and pans, and toilet paper. Back in London in the 1960s at Birkbeck and King's College, and eventually at Oxford since 1973, Roger Penrose continued to publish papers on pure mathematics and on a unified theory, the theory of twistors, combining general relativity and quantum theory. He is the author of The Emperor's New Mind, concerning computers, minds, and the laws of physics, and Shadows of the Mind, a search for the missing science of consciousness. These are popular books where he disputes the trend of viewing mental activity as the carrying out of an algorithmic process. In 1996, Roger Penrose and Stephen Hawking published The Nature of Space and Time. He has received numerous prizes and awards, including the Wolf Prize, the Royal Society Royal Medal, and the Albert Einstein Prize. In 1994, he was knighted by the Queen of England for services to science. I give you Sir Roger Penrose.
Well, today's lecture is entitled Faith. I should make clear at the beginning that it's got nothing to do with religion. The faith I'm concerned with has to do with belief in physical theories and a question of whether one's belief in these physical theories may extend beyond what's justified. In fact, in my lecture last time on Friday, I sort of tackled a big fish, I suppose you could say, and I'll do that again on Wednesday. But today, I'm going to be concerned with a very big fish. That is to say, I'm concerned with the faith that one has in quantum mechanics. Now, quantum mechanics is certainly a subject which is extraordinarily well supported. In fact, there are no observations which tell against the theory. And it explains many, many things which were complete mysteries before the advent of quantum mechanics. In fact, I have a list of a few such things here, a very limited list, but just so you get some feeling for the things involved. Quantum mechanics explains various things like the stability of atoms, spectral lines, chemical forces, black body radiation. I'll say a little bit about 2 of these things here. The reliability of inheritance. In fact, that was Schrödinger pointed out that to make inheritance work, you needed molecules, stable molecules, He didn't know about DNA at the time, but it emerged that this was certainly a very important realization. We know about things like lasers, superconductors, superfluids, etc., 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 and many areas of technology. Combined with special relativity, one gets quantum field theory, which is essential for particle physics. And in fact, last time I gave the same example here, but there are many others. This is the example of the accuracy that one finds in quantum field theory if you do it right. Here is the magnetic moment of the electron according to the theory of quantum field theory, quantum electrodynamics. And here we have the observed value. And as I said before, these figures may be a little out of date, but they won't have changed that much, except perhaps to get a bit more agreement. And you'll see all these figures of agreement between those two. So quantum mechanics is undoubtedly an extraordinarily well-supported theory. The question really I want to raise is whether this gives one enough support to believe that quantum theory is universal. Does it apply to the universe in all its aspects? Or are there likely to be ways in which quantum mechanics must be superseded by some other type of theory? Well, I better say something about quantum mechanics itself first, because I'm not assuming people here know about it, although I'm sure there are lots of people here who do know an awful lot about it. Let me start by mentioning two of the initial puzzles of physics that really led to the formulation of quantum mechanics. The first is the instability of classical atoms, the idea that if you have a classical nucleus with one charge, with a positive charge and these negatively charged electrons going around it, then classically they would simply spiral around, radiate outwards, and they would disappear into the nucleus and you wouldn't have stable atoms at all. So that's a great puzzle on classical theory. And the other famous thing was the black body radiation. But what I wanted to say here is that the basic problem, well, you could say it's Maxwell's fault. Newtonian physics worked beautifully well. One had these particles which interacted with each other, and if the universe was just made out of particles running around, well, that would be fine. But then Faraday and Maxwell found that there were these fields permeating space and time, which were continuous things and had their own existence and had as much reality as the particles themselves. And the problem is that the particles just have a finite number of degrees of freedom and the fields have an infinite number. This is actually an instance of what I was talking about before. So just to remind you, those of you who were here on Friday may remember that I said I was only going to talk about two things in mathematics, basically in any detail, and one of these was what happens when you raise numbers to powers and so on, and you can consider that these numbers can be infinite, and the symbol infinity to the a to the infinity to the b, infinity to the b to the infinity to the c means the freedom in choosing b functions, say the b components of some physical field, freely and continuously on some space of dimension c. And the point was that the c is the crucial thing here. It doesn't matter too much what b is, but if c is the crucial thing. And if you have two such things with different c's, the one with the bigger c is very much larger. So that was really the only point here. But you see this coming up in this particular situation here, because if you want to know how much freedom is there for a single particle in space, well, in order to know how it's going to propagate, you have to know its position and its momentum. So that's 3 numbers to define its position, 3 numbers to define its momentum. So you have a 6-dimensional freedom in this, and the functional freedom is just infinity to the 6th, or infinity to the 9 if you include the fact that it might be spinning around and you have to worry about its axis and where it points and how much the spin is. So that gives you 9 degrees of freedom. And written in this double exponent form, you'd have infinity to the 9 times, well, there's only 0 up there because that's just 1, really. So that's not very huge by the numbers I was talking about before. But if you think about a field, See, what about a Maxwell field or any kind of field? A k component field, well, it would be infinity to the k to the infinity cubed. Sorry, infinity to the k times infinity cubed, I should have said. And you notice here you have a 3 up there, whereas we only had a 0 before. So this number is hugely more than that. And so that means that the number of degrees of freedom in the field is just completely out of proportion to the number of degrees of freedom in particles. So, and if one uses the principle that if you let a system settle down, there's this equipartition energy, which tells you that the energy is distributed between the degrees of freedom, you see that because there's so many more degrees of freedom in the field and practically nothing in the particles, it tells you that the energy gets dragged out of the particles and goes into the fields. So this is basically the problem that's happening here and here. These are just instances of that feature of classical physics. So if classical physics were right, you would have these catastrophes that don't happen because the world holds together and we don't have these problems, and that tells us we need a different theory. So I was really just trying to point out that the problems of classical physics, those particular basic problems, are instances of this thing I was talking about before, about sizes of infinity really depending upon the C here, up there. And in the case of classical particles, you have a 0, and classical fields, you have a 3 up there. So it tells you you've got to do something different. Well, quantum mechanics really resolves the issue by making particles and fields the same thing, in a sense. And so the balance is in some sense restored. Now, this is an instance of what's called wave-particle duality, and the fields you can think of them as, well, they're waves in the fields, if you like. The waves are the fields. And if you can show that in some sense waves and particles are more or less the same thing, which quantum mechanics is trying to say, then you can perhaps get rid of this catastrophe. And the way that one talks about a single particle in quantum mechanics is that that particle has a thing called a wave function, which is mathematically like a physical field. And for a non-spinning particle, this has the freedom infinity to the 3. So you've got a 3 up there now, so you might say that's good news. For the experts, I just have something in brackets here which says that these fields are complex fields. Remember the complex numbers, that was the other thing I specifically pointed out last time. But a complex number has 2 real numbers. So you might think there ought to be a 2 up here to give you 2-component object. But that's compensated by the fact that in quantum mechanics one has to consider things which are of positive frequency. And that balances the fact that they're complex. So you're back at 1 again. I won't go into that. I just thought those of you who know these things already might like to see that point. Okay, so this would seem to even up the battle, if you like, somewhat. But actually, in quantum mechanics, things are more complicated than this. And let's consider, for example, 2 particles. Now, you might think, if you don't know about quantum mechanics, that 2 particles, each one would have its wave function, and so you simply have 2 wave functions. And so that would put a 2 up before the infinity up there, if I can point to it there. You see, you have a 2 there. But that's not what happens. And I'll try to indicate why that's the case. You have to consider a wave function which is a function of 2 coordinates. So you have this kind of function here. And that increases the number at the top. So instead of having infinity to the 2 times infinity to the 3, you would have infinity to the 6. You see, you have 3 components in here, 3 components in there, so you've got a function of 6 variables, and so the functional freedom is this thing over here, not this one over here. So life is a little more complicated than you might have thought. For n particles, you have infinity to the 3n. You see, the n goes up here, which makes life, have far more functions than if it were down there. You might think, where's all that freedom gone? I mean, each time you have more particles, you've got so much more freedom than you had before. And where has it all gone? It's one of these puzzles of quantum mechanics. Well, it all goes into these things called entanglements. And I have to say something about entanglements, because they are very fundamental in quantum mechanics. Some of the great puzzles that you get in quantum mechanics come about from these things called entanglements. I'll come back to that. Well, actually, life is even worse than this. But for a quantum description of an actual physical field, the full description requires an unendingly increasing number of particles. So you'd have something like infinity to the infinity cubed, infinity to the infinity to 6, infinity to the 9, and go on like that, which, well, that's really something like infinity to the infinity to the infinity, which is, roughly speaking, functions on an infinite dimensional space. And also, that happens with particles. So, okay, you do have a balance, but it's a pretty complicated balance. I just wanted to give some feeling for the elaborate nature of quantum mechanics and how much freedom there is in the descriptions of your particles or fields. There's a little point here which I might perhaps mention. You might say, well, if particles and fields are the same, basically, how do you know which is which? Well, you don't really, because you have to use either one description or the other. But I mentioned last time this distinction between bosons and fermions, and there are two kinds of particles. And roughly speaking, the fermions are the ones which are like particles, the electrons and protons and things, and the bosons, photons and so on, are a bit more like fields. That's a rough statement which is more or less true, but you have to be a bit careful. But the distinction between bosons and fermions is a sort of secondary thing. It's very important in quantum mechanics, but the treatment of the two things still involves this kind of hierarchy and so on. So the particles are just as complicated things as the fields. I might mention one thing here which is fairly topical, since it's concerned with a recent Nobel Prize. Tony Leggett got a Nobel Prize for showing that a property that you thought held only for bosons, this was a thing called superconductivity. It's superconductivity or superfluidity? I have to remember which it was. But anyway, it's supposed to hold only for bosons, and it seemed that this helium-3 had this superfluid, I guess it is, property in the case of whereas in fact it's a fermion, and it shouldn't, you see. And there was an interview with Tony Leggett over the radio, which I just happened to catch. It was just a very short interview. And they were asking him about the work he'd done for the Nobel Prize, and he said, I found this quite interesting, he said he knew about this property that these fermions, which shouldn't have, because they're fermions and they ought to be bosons to have this property, and he thought this meant that quantum mechanics must be wrong, and all he had to do now was to prove it was wrong convincingly. And he then thought out various ways that it could slip through, and it turned out one of these was right, and got him the Nobel Prize. So what I find interesting is that he has this, you see, I mentioned there is this sort of faith in quantum mechanics. He evidently didn't have that faith and thought that quantum mechanics was something one should try and maybe see how it couldn't be true at some level. And you might ask why he felt that. Well, I'll come to this sort of thing shortly. Now, quantum mechanics, I've just been confusing you by telling you all these infinities. So let me tell you what quantum mechanics is like. So I have a picture of quantum mechanics here. This picture I drew for another lecture which I gave a year ago, and here it is. I was invited to give a talk in Denmark, in Odense, I don't know how you pronounce it, but which was where Hans Christian Andersen was born and lived. And since I'd written a book using one of his stories in the title, The Emperor's New Clothes it was, but The Emperor's New Mind was the slight variation, I thought, well, I'd better not use that one, but try and think of another Hans Christian Andersen story to illustrate something which I might speak about. And it occurred to me that the mermaid is actually, in many respects, I won't go into the other ones, but in many respects, a good analogy to use for quantum mechanics. So I'll have to explain that, you see. Well, what about the mermaid, you see? Well, this was a new angle on the basic paradox of quantum mechanics. what is it about the mermaid? Well, you see she's partly fish and she's partly human. And you'll see that one end of this picture, the bottom end, is a great entangled mess, and that it represents quantum mechanics. That's the quantum world, if you like, down there. And the classical world is up at the top, where you have discrete entities. You see, I said entanglements. In some sense, according to quantum mechanics, you don't have these separate things. They're all entangled in some sense. And that was the picture was supposed to indicate that down here. And yet at the classical side, you have this world with discrete, separate things which behave in ways which are more familiar to us. And the mermaid, there's something magical about her. She somehow straddles the two worlds. And she, in a sense, represents the third aspect of quantum mechanics. Let me give you that first. So we have the classical and the quantum worlds, and we have laws which they each act according to. The classical world acts according to classical physics, and that's the C I've got up here. The quantum world acts according to what's called unitary evolution, and there's a system of equations which govern the behavior in the quantum world. But that's not the whole of quantum mechanics. There's something else which has to do with how you get from one level to the other. Roughly speaking, the quantum world is to do with small things. So you might say atoms, molecules, fundamental particles, and so on. And the classical world is to do with large things like this thing and so on. Well, that's a bit misleading, but nevertheless, in practice, that's what happens. But you need this way of getting from one world to the other. And that's represented by something where I've used the letter R. Think, for example, of a Geiger counter. A Geiger counter, a quantum particle enters it, and it makes a click. And the click is a classical level thing. So you're getting from one level to the other. And the process whereby you describe that, it's called the measurement process, or the reduction of the state. The R is to do with the reduction of the state. So you have a description which sits down here. That's the wave function that I was talking about before. And it evolves normally in the quantum world according to this U process. But every now and again you do something quite different, which is this other process. And you notice that the arrow for the R is pointing. That's where the mermaid is, you see. So she represents how you get from one level to the other in this picture. Now, there's some words which describe these processes here. Classical physics, as most of us may be familiar with, is deterministic. That is, the laws, if you know what the state of a system at any one time, the laws tell you what the state of that system is later on. But the quantum level also is deterministic. There's this equation called the Schrödinger equation, which is a deterministic equation. But there is this other process, which is how you get from one level to the other, which is the reduction of the state, or the measurement process, which is non-deterministic, and all the randomness comes in at that stage. Now, the point I'm making here is that U and R are mutually inconsistent. Well, they're certainly it's sort of in the blatantly are, if you like, because after all, U is deterministic and R is non-deterministic. So it's a little difficult to see how you could get something involving randomness out of a completely deterministic equation. Well, I'll say a little bit more about that. It's called the measurement problem, if you like. But I mentioned Tony Leggett before, and he used the phrase the measurement paradox, which I think is in a way a better description, because it really is a contradiction between these two processes. And the reason that Tony Leggett was looking for a flaw in quantum mechanics was that he thought that there was a real paradox here which needed to be resolved in some way. Well, let me say a little bit more about quantum mechanics and the rules of quantum mechanics. I have here another transparency which illustrates a different way of looking at the particle and wave aspects of a quantum entity. At the top, we have the particle behavior. You have, imagine, a source. Let's imagine it's a photon. So here we have a photon source. Photon goes along. It hits this thing. You can call it a half-silvered mirror, if you like. It's officially, it's what people call a beam splitter. So the photon goes along here, or it might go along here, and we'll imagine detectors here and here, and the particle aspect of this thing is exhibited in this type of setup, because what you find is that either one detector or the other one registers the particle, not both, not neither. I should say this is an idealized situation. In practice you might find sometimes misses it altogether, but in the idealized situation it's either A or B, and it's a rigid exclusive one or the other. And that's just the way you would expect a particle to behave. But if you set up something like this, a sort of interferometer, where we have the same beam splitter here, and now proper, fully silvered mirrors there, and another beam splitter here, and let's suppose these path lengths are all equal, what you find is that somehow it's always this detector which receives the photon, never that one. That somehow the two possible things that the photon might do, it might go this way, it might go this way, somehow mysteriously cancel each other out as far as this route is concerned, and they reinforce each other as far as this route is concerned. Now this is the kind of thing that ordinary particles don't do, but waves would do it. So if you imagine these were little ripples, and then they'd be split into two, and then so on, and they could either be coherent or be the opposite. They could either cancel or add, and you could get this sort of behavior. But what's very hard to see is how you can get this behavior and that behavior with the same physical entity. That's the puzzle of quantum mechanics. And the way one resolves this issue is by adopting a rather extraordinary procedure that is indicated here. If you have two things, let's talk about it with the second picture here. You have two things which might happen. Alternative A, and that alternative A is going the top route, like that, and alternative B is taking the other route. That in some sense, quantum mechanics says they both happen at once. So as long as you're at the quantum level, you have these two things, and they somehow coexist. And you have to get used to that idea, that different things can coexist in quantum mechanics. And what you tend to do is you add them up in this way. Alternative A is one of the things, alternative B is the other thing, and you say they coexist, but there are also these multiplying coefficients there. You might have thought those were probabilities, which say it's a certain probability it does A and certain probability it does B, but that's quite wrong. If it were probabilities, you'd never get the kind of cancellation that occurs here. And in quantum mechanics, the way one deals with this is to use these complex numbers. Well, that's the other thing that I mentioned last time, that you had to know. The two things you had to know are about these exponents and so on, and about complex numbers. Well, here's the complex plane again, where you have I as the square root of -1 coming into it. It's one of these great miracles that this wonderful idea, which has a great fruitfulness in mathematics, turns out to be out there in the world in some sense. And it's a wonderful example of the unity between physical world and mathematics when you get the mathematics right. This is a key thing. It's not every piece of mathematics which seems to be reflected in the physical world, but certain things do seem to be reflected in the world to an extraordinary degree. And this is an example of this, one of the clearest and most powerful examples. Now that's the process U, which I was talking about, where these superpositions are somehow preserved. They just keep on being preserved. I'll say a little bit more about that later. But when you adopt the other process, the R, the thing which comes in the measurement process, you suddenly change the rules. And you do what's taking the squared modulus of these things, this funny symbol here. That means the square of the distance in this plane to W and the distance to Z. You take the square of each. Square of the distances, it's the squared modulus, as it's called. And the ratio of those two things become the relative probabilities for two things to happen. So if you actually try to measure in which route was that particle, you'd have to do this process here. Well, that's something completely different, and okay, you've got probabilities. It's not deterministic. It's a completely different rule. And that's the measurement paradox, is to try and understand how these two things can coexist. Well, let me say a little bit more about this adding business up here, because that's rather important. It's an example of what we call linearity in physics. Let me give some illustrations here. You're probably familiar with this idea that in Newtonian physics, as far as I'm aware, this was first due to Galileo, that you take forces and you add them up. You can do this by the parallelogram. Let's say there are these three forces acting here. You can add these two up by the parallelogram law, and then add that one to that one by the parallelogram law, and you get the sum there. So that's the way you add these vector-like quantities. Or else you can take components in three independent directions and just add the components. It's the same equivalent thing. Now you see, we know things in physics. Okay, the Newtonian forces add up, but something else which adds up are the Maxwell fields. You can take the electric field or the magnetic field. I've done the electric field in purple and the magnetic field in green, and you might have two things which you add up to get the third, and I've done that all the way over. But you see, these are fields. At each point, you add them up according to this parallelogram law, and so on. So this, you get linearity of the Maxwell fields, electromagnetic fields. That's a striking feature that Maxwell's fields have. They add up. You can have one field and another field, and you can simply add them in this way, and the way in which they propagate is consistent with the way in which they add. And that's a statement of linearity of the Maxwell fields. In a similar way, the Schrödinger equation, which governs the time evolution of the quantum state, is linear. But there's a difference here. It's complex linear. So here's this complex thing again coming in. Well, I thought I'd just give you one example where this is a very striking feature. It kind of fits in with other properties of the world in extraordinary ways. And I'll just give you the example of a spin-half particle. Well, the examples are given here. An electron, or a proton, or a neutron, or a quark. And they all are what are called spin-half particles. And they have this property that you can add, in a certain sense, spin up. So you might imagine that the particle is spinning right-handed about the upward direction. That's what you mean by spin up. So it could be spinning that way. Or it could be spinning down, which means right-handed about the downward direction, or if you like, left-handed about the upward direction. And if you take those two alternatives, then you can add them together using this complex linearity. So I've got the W and the Z here, which are multiplying coefficients. Now there's a rule, I should say here, which is particular to quantum mechanics, which is that you don't care about an overall complex number factor. What it really means is that all you're interested in is the ratio between W and Z. And the miracle here is that the complex linearity spreads you over the whole sphere. So you could have spinning up, spinning down, and all the different other alternatives are these complex combinations. And the geometry is illustrated by this picture here. If you want to describe the direction out this way as a combination of up and down, well, you look at these coefficients here, and you want to make the combination so that U is Z over W. That's the ratio of these two. And U is some point in this complex plane that I was showing you before. And then you stereographically project to the sphere. So you take the south pole, join that to this point here, and you get a point on the sphere here. And then the line out from the center is the direction of spin that gives you. So you get all the directions of spin from just these two. If you get up and down, and you create all the others by just using this wonderful complex linearity. So I just want to show you that in some circumstances, complex linearity is beautiful and fundamental to the way in which particles behave. So it's a good thing. But now let me tell you something else about complex linearity. I just tell you more or less how it works. See, let's take something more complicated. Here we have a photon going up this way and hitting a green thing and producing a whole lot of junk. Don't worry about what it is, it doesn't matter. It produces a whole lot of junk up there. Another thing it might do is it go out sideways, hitting a brown thing and producing a whole lot of different junk. Now, the linearity of the Schrödinger equation tells you, if you set up the following situation, which you could do by having a beam splitter here, so the photon now is in this superposition of these two different routes. And remember from the example I gave you before, right at the beginning, this is something you have to take seriously in order to get these effects here. But it tells you in this rather stupid experiment that this green possibility and the brown possibility have to be in superposition. Now, I'll come to the troubles that causes in a moment, but before doing that, let me say just something about the entanglements. You see, this is a feature that gives rise to entanglements because you can have complicated things happening here involving many, many particles. And say this one and this one here, these might be two different particles. And they're in some sense entangled because whatever happens to this one is correlated with what happens to that one. But then that's sort of on top of what happens over here. It gets a little complicated, but the implications of this give you some of the most extraordinary things in quantum mechanics. And I'll just give you an example here. This is something known as quantum non-locality, which was originally, I guess, pointed out by Einstein. In fact, when he was trying to, like Tony Leggett, he was trying to show there was something wrong with quantum mechanics, and he tried to give examples a bit like the one I'm describing here. This particular thing was, somebody told me this was actually Einstein's version, but it wasn't the published version. This was actually due to Bohm. You could imagine an object of spin 0 in the middle and two spin half particles going out in opposite directions, and then you measure the spins in different places. And what you find, according to a famous theorem due to John Bell, is that there's a conflict between any local realistic model. So you say, well, this thing over here is somehow independent of that thing over there. That just doesn't work. What you find is that whatever this thing is, and whatever that thing is, they're both part of one quantum object which stretches from one side to the other. And you can actually, John Bell pointed out that there were important examples where you couldn't explain this in any other way. There are experiments that were performed later, one of the most famous due to Alain Aspect in Paris, and this involved photons going in opposite directions to a distance of something like 12 meters. So what it showed was that over a distance of 12 meters, in different corners of the room, the two photons were still one quantum thing, even though they were widely separated. More recently, there are experiments, well, this says 10 kilometers. I believe that's not the record now. It's probably something like 15 kilometers or maybe even more by now. There are examples where photons can be separated over huge distances and still behave as a single quantum entity. One thing that's interesting about that is it's telling us that quantum mechanics is not restricted to tiny distances. It does stretch out over huge distances. I don't know, it might be worth quickly giving you this, but I probably shouldn't spend too much time on it. There's a very nice example due to Lucien Hardy of this sort of Bell inequality thing. Let me just tell you how it works. Those of you who know about these things, I should say there's a spin 1 initial state, but let's not too worry about it here. Roughly speaking, you have two black boxes here, each containing a particle of spin half, and you're allowed to measure the spin on this one and this one. And I didn't say this, but if you want to measure the spin of a spin half particle, you have to choose your direction first. Say, well, I think I'll measure it in that direction. Are you spinning that way or this way? And it has to decide whether it's that way or that way. And if you chose it right, in order to avoid too much confusion here, let's go back to this thing here. See, if it was that state of spin, and I choose to measure its spin that way, it would have to say, yes, I'm spinning that way. But if I chose to measure spin that way, it would give me a probabilistic answer. We're saying, well, if it was exactly that way, it's 50% that, 50% that. If it was some other direction like that, it might be, say, maybe 70% that way and 30% that way and so on. But let's not worry about the details too much here. In the example of Lucien Hardy's, you don't have to worry about that too much. That's what's nice about it. All you have to know is that with this system, with these black boxes, if you measure up, down on this side and up, down on this side, you sometimes get down, down. That is to say, sometimes you see there's something in the middle which shoots particles into these boxes, and these particles have to know that at 1/12 of the time to produce the answer down, down, if you measure up, down, up, down. But the rules also tell you that what never happens is down over here and to the left over here if you choose to measure up, down, and right, left. What that seems to say is for this case, you see, they've got to be prepared to give down, down if the two people are making measurements on either side each measure up, down, up, down. Okay, so they've got to be prepared to do that. But suppose the one on this side measured up, down, and the measure on this side measured right, left, then it would never be down on this side, but you're going to get down on this side, you'd have thought, because of that. So therefore, it's got to be to the right. And you never get to the left on this side and down over here, so you'd have thought the one on this side then has to be to the right if you measure right, left. But you never get that. I won't bother to go into this in any detail. You can ask me afterwards if you're interested. But it's a very nice example where the contradiction is absolutely blatant. You don't have to know anything about probabilities apart from just the fact that it sometimes happens. The fact this is a 1/12 is not important. So you have to know sometimes the system is going to give you a down, down for two up, down measurements. And this contradicts the contents of the boxes being independent objects acting without communication or foreknowledge. So this is an example of quantum entanglement. I was trying to tell you about the entanglement, and entanglement has these rather subtle implications. Surprising, because they tell you that separated things are still in some sense connected, but subtle. And this is, you might think that, you know, all this huge amounts of freedom in these states for two particles. Remember, it was infinity to the 6 when we talked about particle pairs instead of infinity. Where's all that extra freedom gone? It's one of the puzzles of quantum mechanics. Well, let's come back to that later on. But let me go back to the issue which I brought up before, maybe the linearity, and said, okay, what about this? Quantum mechanics has this linear property. Is that anything to worry about? Well, Schrödinger worried about it. And let me start now by giving you a simple experiment. Here we have a source of a photon over here. I've got a bit more modern here. This is the laser rather than the light bulb, but never mind. Source of a photon here and a detector over here. So the photon goes zipping along and the detector detects it. Well, there's nothing paradoxical about that. Rather boring, in fact. So let's make it a little more interesting by attaching a gun to this from some murderous device and a cat, and the poor cat is put to death by the device. Well, that's not very humane. I should tell you that these are all thought experiments. They're not things that not recommended that you actually do the experiment. But it sort of Schrödinger, who was a very humane person, I'm sure he never did the experiment, but he liked to put it in this rather dramatic form. But still, we can be a little kinder to the cat by inserting instead a mirror there. And so the photon goes sailing off up at the top, and the cat's fine. So that's okay. Except that might not have been a mirror, that might have been a beam splitter. And remember about our quantum linearity. What that tells us is that the two alternatives, photon going this way, cat alive, photon going this way and cat dead, have to coexist in superposition according to quantum linearity. So quantum linearity tells us that we could produce cats which are in superpositions of life and death. Well, sometimes if I'm in a bit of a hurry, I stop at this point. You're saying, isn't this ridiculous? And Schrödinger was saying this to show that it was ridiculous. And Schrödinger, it's fine for him to say that because it was his equation after all. And he was more or less saying, don't believe my equation when it's applied to cats. Well, that's fine. But sometimes when I give this, my colleagues say, no, you've been a bit sloppy here. You haven't taken into account the environment. So, well, for this lecture, I especially wanted to make sure I did that. So here we have, I think the dead cat, just not that it makes much difference. Here we have the poor dead cat, and it has to have an environment as well. Okay, so there I put it there. Now what about the live cat? Well, okay, the live cat, sorry, yes, the live cat, it needs its environment too, so here it is. Now you may not notice much difference. I assure you that those little particles, air particles, are in different places. And just so you know they're different, I've done them in a slightly different color, but that's just to help you. They're not really a different color. They're meant to be the same color as the environment spots in the other picture. And what does quantum linearity say? It says that you get this. Not just the cat being in a superposition of life and death, but all those environmental particles being in superpositions of different places too. Doesn't seem to help very much, does it? Well, the official thing you're supposed to do is worry that you don't know where the environment is, and so you do some process called summing over the unknown states and so on. Well, it doesn't, you can do that if you like, but it doesn't really help, because you're supposed to have some state, even if you don't know what it is, there should be some state that the system has. Okay, it may not be that's the whole issue then. Suppose somebody comes along. Let's go back to the dead cat again. I think that was the first one. Okay. I'm getting very complicated with all these. Here's the dead cat. Somebody might come along and look at the cat, you see here. So I have an observer coming along. Maybe that's the key thing. An observer comes along, looks at the cat, and I've got even represented part of the state of mind of the observer, which is the observer seems to perceive a dead cat. So we could, perhaps this is part of the quantum state too. You don't have to know what the observer's mind is registering, you just have to look at the observer's expression. You see there's a rather grumpy looking face there, whereas in the case of the live cat, well, yes, the observer comes along and looks at it. There we have the cat. And you'll notice that the observer is rather happier in this case. So, okay, there is a bit of difference. Needn't be huge. But the thing is, what does quantum mechanics say? Well, the observer is only made of material and all that sort of stuff, quantum particles and so on. So that observer ought to be involved in the superposition too. So this is the description that one is led to. I can get these things properly on top of each other, I hope, with a somewhat mixed expression and a certain mixed perception. It doesn't really help. What about you? You could put the environment in as well if you like. Here it goes. I mean, none of these things really make any difference. Well, you could say that, and people do, and this is the many worlds interpretation of quantum mechanics, which says that indeed the observer would be put into a superposition, but that kind of observer perception is not allowed for some reason, and the observer state splits, and there become two universes, one containing one observer and the other containing the other observer. Well, there's nothing in this which splits, I should say. It really is a superposition still, even if you believe it applies to the whole universe. Now, it is a view which is very often expressed about quantum mechanics, and it's called the many worlds view, which says that somehow this is what happens, and it's supposed to make sense of it. Well, the idea is, I suppose, that for some reason, perception states, whatever they are, aren't allowed to be this, and you're allowed to perceive one or the other. And it's not explained why perception states have to have that form. What I particularly don't like about the many worlds approach, I can see you're forced into it. You see, if you believe that U holds at all levels, you are driven to this view. So this is where quantum mechanics takes you, if you like. Or it does if you believe that it's a consistent theory in which U is the only thing happens, unitary evolution. And the resolution, according to many worlds, is that somehow you have to understand that perception doesn't do this and it singles out one of these universes. It's conceivable that that is in a sense, correct. The trouble is, it seems to me, that you're pushing your very precise physics. It's one of the things about physics. And all these rules that one's applying, they're very, very accurate, extraordinarily precise. And you're pushing it into an area that we know absolutely nothing about. We don't know anything, very little about consciousness, what it is, and why one should get the probabilities of quantum mechanics out of this thing that we know nothing about. So it's conceivable it's the right answer, but it would be a sad thing if it were, because we'd have to know a lot more about things that we're further from understanding than we are about quantum mechanics. So let's, I would take the view that this is virtually reductio ad absurdum. As Schrödinger was trying to say, I think, that there is something wrong with the standard unitary evolution view, or the Schrödinger equation, if you like. Let's address some of the major views about quantum mechanics, the sort of ontology of quantum mechanics. I should say that I could spend about, not just the rest of this talk, but probably about 3 or 4 hours going into all the different ontologies of quantum mechanics. So I've only put a very limited list here, but perhaps the most usual points of view that are adopted. First of all, I should make the point that it makes no sense to take a U-evolving, that is a unitarily evolving state vector, psi, don't worry about these funny brackets, that's just for a different lecture basically, state vector psi as describing the reality that we perceive about us. You see, the many worlds says it isn't the reality we perceive about us because somehow perception does something funny at some level. But what is the Copenhagen view? This is the standard quantum mechanical view, if you like, Niels Bohr and company. It says there is no quantum level reality as described by the quantum formalism. Psi describes instead the experimental's knowledge, that in some sense it's all in the mind. And it's all in the mind, if you like, because ultimately a measurement is made by a being with a consciousness. Well, it's sort of, again, driving you to this view that you have to know about consciousness before you can interpret quantum mechanics. And here's many worlds, which I was just talking about before, that a U-evolving state vector does describe reality according to that view. It's completely different, if you like. You see, the ontology is quite different. Here we say psi doesn't describe reality. Here we say it does. But all outcomes of an experiment coexist, and each accompanied by a different mental state of an observer. And somehow that's meant to resolve the issue. Or you can take a pragmatic view, which is somehow the environment just makes life so complicated, so you give up, do something else, and that's quite a usual view in quantum mechanics. It gives you the right answers, so that's fine. You say you're not interested in ontology, that's just for philosophers. Well, you can take that view and certainly make progress that way, but it's not very satisfying if you really want a picture of what's really going on in the world. My own view is the one in red here. Quantum mechanics is a provisional theory, and that these things I've called U, R, and C, there is some kind of hybrid. That is a hybrid, you see, but that's to be superseded by a new theory. And what we require is something which is a major revolution. I think it's worth giving you the view, not just of Schrödinger, I told you about him, but one of the people who is usually considered as the sort of person who set quantum mechanics in the form that we use it more than any other person. He established the way it's used and so on. This is Dirac. Dirac, in fact, those funny brackets which I didn't describe to you, that's his idea. And a very good idea, actually. He talked about quantum field theory. Dirac believed that the infinities were fundamentally flawed and a new theory would be needed. I talked about the infinities at the last lecture. I'm very disturbed with the situation because so-called good theory, that's quantum field theory, I suppose, does involve, sorry, let's read it from up there, neglecting infinities in an arbitrary way. This is not sensible mathematics. Sensible mathematics involves neglecting a quantity when it's small, not because it's infinitely great and we do not want it. That's a very, very Dirac statement. Absolutely clear, absolutely to the point, and beautifully simple. I mean, there's no question there. That's very Dirac. And here another statement. Dirac was not interested in the problems of interpretation of quantum theory, e.g. the measurement problem, regarding quantum mechanics as a provisional theory. And this the famous Bohr-Einstein debate, which it's considered that Bohr won. Einstein trying to show that quantum mechanics had a flaw, and Bohr each time being able to refute what Einstein had suggested. And this is Dirac's comment on it. I think it's very likely, or at any rate quite possible, that in the long run Einstein will turn out to be correct, even though for the time being physicists have to accept the Bohr probability interpretation, especially if they have examinations in front of them. You're right to the point again. Okay, well, let's just end by trying to tell you what I think. Now, you see, where are we? I have to find the right picture. They've all got messed up here. Let's go back to this picture here. And instead of putting a cat here, you see, it's all right for dramatic purposes, but not only is it a bit inhumane to kill a cat, yes, and even worse, I suppose, to put it in a limbo of life and death or something, but it's also unnecessarily complicating the problem, because the cat, you have to worry about the cat's consciousness, all sorts of things you have to worry about which are going to make your physics more elaborate than you need to. So let's simplify it and consider a lump of material here. And instead of killing a cat, I just say if it goes this way, it moves this lump of material from one place to another. If it goes the other way, it leaves that lump of material alone. Now, I'm going to call a theory which says that, okay, unitary evolution isn't completely accurate. The linearity of the Schrödinger equation is an approximation. We know already that well, I mentioned before the Newtonian adding of forces, and in gravitational theory you might say, well, linearity is a wonderful thing. Well, it is. That's in order to get Newtonian gravity to work, you need that. But then Einstein comes along with a completely different set of ideas. They agree with Newtonian mechanics to an extraordinary degree. In the places where it differs, Einstein's one turns out to be accurate. And there you have nonlinearity, where previously you had a linear adding of forces. In the Einstein case, it's fundamentally nonlinear. So the suggestion is that somewhere along the line, there are going to be nonlinearities in quantum mechanics. That linear rule, beautiful as it is, will be replaced. And people often say, well, wasn't it ugly to spoil that beautiful linear law? Well, it is if you just do that. If that's all you did to Newtonian theory, it would be a mess. But Einstein had another perspective on Newtonian theory, which gave something else which was even more beautiful in its way. So I would expect that what's going to happen to quantum mechanics eventually is some revolution of the same magnitude, at least, as that which Einstein brought to gravitational theory. But let me also say that I think that gravity has got something to do with this change. And I'm going to use the acronym OR to stand for objective reduction. So the reduction process, the R thing, which I showed you before, some people would say it's kind of an artifact, it's all in the mind or what have you. I'm saying it really is something which happens in the physical world. It's objective. The reduction of the state means that the Schrödinger equation doesn't keep on evolving in the way that it should according to the Schrödinger evolution, but suddenly jumps and does funny things. Okay, that's something real about that. And so objective reduction, well, it's a very nice acronym because OR spells OR, so it tells you the cat is either dead or alive. Or in this case, the lump of material is either in this position or in that one. And the idea is that there's some sort of instability, that the superposition is unstable and reduces to one location or the other in a time scale that you can calculate if you know the mass distribution in each of these. What you do is to take these two mass distributions, you consider one to be positive and the other negative, or if you like to subtract one from the other, take what's called the gravitational self-energy of this difference. It's usually a very small energy, but we call this Eg. And what I say is that H cross over Eg, this is basically Planck's constant divided by this energy, is the time, or is of the order of the time that this thing can persist for, that it will decay into one or the other in that time scale. And there are reasons for suggesting this which come from the principles of general relativity combined with those of quantum mechanics. And I'm not going to tell you here, although I say something about it in a colloquium tomorrow, but just to give you a sort of cartoon of what's going on here. The idea is that you've got a superposition of two locations, and then you consider trying to draw a space-time diagram of that. Initially, it's one lump location, causes a bit of distortion of the space-time. As time evolves, these two distortions disagree with each other, and there's a certain tension between trying to, well, one of these space-times and the other, and trying to superpose them gives you this instability. Now, when I talk to physicists about this, the reaction that's very common is, well, look, that's ridiculous. Gravitational forces, gravitational attractions are so ridiculously tiny, and particularly when you involve them with quantum mechanics, you've basically got quantum gravity, and the effects are so tiny that why should you expect to see anything measurable at all? So here I'm saying, but surely quantum gravitational effects are far too tiny to have any relevance to ordinary scales. And one might mention the Planck length, I think I said this in the last lecture, which is 20 orders of magnitude smaller than the scale of ordinary particles, 10 to the minus 33 centimeters. The Planck time, which is 20 orders of magnitude smaller than the fastest particle processes, 10 to the minus 43 seconds. It's a ridiculously short length of time. 20 orders of magnitude below the tiniest particle physics processes. But these arise from multiplying together two quantities which are each on an ordinary physical scale very tiny. One of them is Newton's constant, which is very tiny, G, gravitational constant. The other is this thing h cross, Planck's constant over 2 pi, which on ordinary scale is also very tiny. And if you take two very tiny things and multiply them together, you get something ridiculously tiny, which is the sort of thing you're getting here and here. But in this particular suggestion I'm making, you don't get that. You get something which I said before is this h cross divided by Eg. Eg is a gravitational energy. It involves a gravitational constant. Basically, you're dividing one of these very tiny quantities by another very tiny quantity, and you just have to work it out in any particular case to see whether that's going to be something of a significant size or not. Well, there is a proposal which is being embarked upon by colleagues of mine who are now at Santa Barbara, and I'll just end by telling you the rough idea behind this experiment. This experiment is to try to see whether gravitational law is correct or not. And I mentioned a few people here involved. The original idea was partly stimulated by Johannes Dapprich and lots of suggestions by Anton Zeilinger and his colleagues. But it's Dick Baumeister, Will Marshall, Christoph Simon, and other colleagues who are involved in performing this experiment. The version I'm going to give you here is a simplified description. What they're doing is something much more sophisticated than this, but I'll just give you the rough idea, and it's something that you can understand on the basis of things I've just been saying earlier. Here you have a laser sending out a photon. There's the beam splitter, the same old thing I've been talking about. This photon then goes along this way and this way. It's a superposition of these two alternative things it can do in quantum mechanics and experiment. Certainly tell you that photons can do that. It comes along this way and it hits this little mirror here. I've tried to magnify it here to indicate the crystal lattice. And it hits it and only gives it a tiny little knock, a knock which is just enough to displace the nuclei from each other. Or I should say that the red ones indicate the unmoved position and the blue ones the displaced position. And so the nuclei will be slightly displaced in this experiment. To give it enough kick in this experiment, these are ordinary visible light photons. I tried first of all to think in terms of X-ray photons, but the problem there is to keep them under control appropriately, which is very difficult. But the idea here is that you take an ordinary visible light photon and you bang it on this little mirror something like 1,000,000 times. The description that my colleague Will Marshall gave me is, imagine a diving board with somebody jumping up and down on it, you see. You've got to jump up, it's this photon jumping up and down on the diving board 1,000,000 times, and that gives it just enough kick to displace it in the sort of way indicated. Now the idea is, it's got a little spring here, you see, and it does that, and this bounces back after a little while, and just as it does that, you somehow have to get the photons out, or the photon, I should say, it's two instances of the same photon, out. You keep this one in some kind of a cavity, a million times bouncing backwards and forwards, and likewise down here, and then you have to get them out, and the idea is that once this has gone back again, it's as though nothing had happened, and the photon, these two beams will combine and go back again into the laser. Whereas the detector over here would only detect it if something has gone wrong with the quantum mechanical situation. And the idea is that if this at some stage becomes one or the other, then you will sometimes see the photon going up this way. Of course, it's a very difficult experiment, much more involved than I'm indicating here. The size of this little mirror in the thing they're doing at the moment is something like 1/10 of the thickness of a human hair. You could just about see it. It doesn't get very much moved, only a nuclear diameter, roughly speaking. But you can't look at it, because if you did, that means you have to use some light to illuminate it, and that would spoil the experiment. So you have to do this all very indirectly, and you'd have to do the experiment many, many times. The idea is that in something like the order of about a second, according to the formula I gave you, this would become one or the other, in something like a second. So it is a reasonable length of time, and in this situation, you get a reasonable length of time for that ratio. Now, of course, it may be wrong. Maybe quantum mechanics comes through unscathed again. On the other hand, there's a chance that something like this would show up something new. It would be the first time you really have a place where principles of quantum mechanics and of general relativity are somehow, there's a kind of tension between these two, and you're beginning to get to the region where this tension manifests itself. There are more specific reasons I could give you for why I think that this decay time is appropriate in this situation, but perhaps not appropriate for this lecture. So I think I'd better leave it at this point. Thank you very much.
Let's see, we have time for questions. There's one over here. There is a microphone around, so wait until you get the microphone before you ask the question.
Thank you. What could you say about Bohm theory in connection with all this?
Yes, well, it always seemed to me that Bohm theory, as all these theories go, the ones I mentioned, but there are others too, and Bohm theory is one of them, or de Broglie-Bohm theory perhaps, it has a reasonable ontology. I think all the others have problems with making some sense of what reality is supposed to mean within the theory, whereas the Bohm theory does seem to make some sense. I have difficulties with it. It seems to concentrate on position space. Well, some other ideas do too. I thought I had much more serious objections until I was visiting the Perimeter Institute in the summer, and I met Anthony Valentini, and he explained his way of looking at the Bohm theory, and I was rather disconcerted to find that I couldn't see anything wrong with it. So it does seem to me that it's perhaps the one conventional, in quotes, theory that is conventional in the sense there are no new predictions, in which the ontology does seem to hang together. So I don't altogether like it. I think there's the various artificial things about it, but I can't give a really kind of watertight objection to it. It may be that it's a theory which, maybe it's right. But it would be a little bit awkward if it is right, because it doesn't give any predictions different from standard quantum mechanics. You'd like to have some theory which says, no, you're going to see a difference here or there. And in the experiment I'm suggesting here, there is a difference proposed. There's nothing gravitational in the Bohm theory either. I think I have to think about it some more. I have a sneaking feeling that I'm not going to be as happy with it when I thought a bit more, but I can't say that at the moment. But it's certainly something well worth taking seriously.
Let's see, any other question? There's one here.
Yes?
I'm a student of yours from 1968 in Birkbeck College.
Oh, I see, yes.
King's, actually.
Hello. Yes.
Just wanted to ask what time interval must go past before we can expect to be revolutionized?
Yes. Well, the trouble with that is, when I asked Dick Baumeister this, you see, he's a very cautious person, and all I can do is try and judge from the expression on his face. And it's, he doesn't give any secrets away. I can only give you real guesses here. The thing is that the experiment that they're doing at the moment actually falls short of what I need by several orders of magnitude. You know, maybe about 5, which sounds like a lot. But if they can get this experiment working, and I think there's a reasonable chance, say in a couple of years, they would get it working, it would, if it agrees with quantum mechanics, and I expect it to, at that level, it would give us, by a factor of something like 10 to the 12, the record-sized Schrodinger's cat. The record at the moment is, I mean, maybe somebody else will get the record in the meantime, but the record at the moment is held, as far as I know, by Anton Zeilinger and his associates, where they've done 2 slit experiments with C60 and C70 buckyballs, these carbon-60, carbon-70 things, and they behave according to quantum mechanics. But you see, that's, according to me, is way down at the level where, yes, quantum mechanics should be fine. This is stepping up in mass from that by a factor of, I think it's about 10 to the 12. Now, if they can do this, even if it confirms quantum mechanics, as I expect, it would be a great achievement, because it certainly would be the biggest quantum superposition ever seen. Unless, as I say, somebody else does a better one in the meantime. But then they've got to improve it. And that's anybody's guess. Probably they're going to have to get better mirrors than they're using, which are already something like 1,000,000-fold reflective, and they've got to up that a bit, cool it way down. They'll be doing very low temperature experiments, and they'll be able to pick up a few orders of magnitude in there. I suspect the thing is, once they gain the experience, they will think of ways of moving ahead. But there's a big question mark there. I mean, how much longer they would need? Do they need another 5 years? Is that enough time? Will it work at all? I can't say. I'd like to know the answer to that question.
Let's see, there's a question there in the back. Wait until you get the microphone.
How does the gravitational OR affect your understanding of entanglement? Or affect your understanding of entanglement, if it does at all?
Yes, sorry, I've made it, that's good, thank you for asking that. Yes, the view, you see, I suppose it's back to the mermaid and all that, you see. You have the entanglements down here, and it's in these EPR situations. See, what happens, you have 2 particles going to different corners of the room. You make a measurement over there, and once that measurement is made, it cuts the entanglement free. Now, you see, normally people would take the view that making a measurement, it just entangles the apparatus with it too, and so it's just the worse and worse. And one of the problems with quantum mechanics, as we understand it now, is that these entanglements simply spread out through the universe, and there's nothing to control them. I don't see that you'd get anything like ordinary physics coming out of large systems. You don't. The sort of conventional view, I suppose, is that large objects behave classically. But there's no evidence for that. Large objects will just get worse and worse with entanglements. Now, the view here is that state reduction cuts them loose. So a measurement over there of one member of the CPR pair will cut loose the one over there. And so the entanglements are broken when one makes a state reduction. And this is happening all the time, which is why we see these discrete objects out here in the classical world, why it's not all entangled up here. But you need state reduction to be a real process. And going back to the degrees of freedom, I talked about these, enormous numbers of degrees of freedom that one gets in quantum states. They would also, somehow your information gets spread out all over these things, and why don't you just get an incredible mess? Well, all the time, it's the measurement process which somehow reduces it back down to a classical picture. Maybe there's something unstable. You see, if you have nonlinearities, these extra degrees of freedom could be unstable, and they die away in some sense. So the view would have to be that the OR cuts loose what your system was entangled with previously. Now, there's no theory. I'm just saying that for simple systems like the ones I was considering, where you have a superposition of an object over here and over here, that I give you a prediction as to how long that superposition will live. But it doesn't tell you what to do with general quantum processes. How do they become classical-like? How do the entanglements get cut? But I certainly believe that that has to be part of a missing theory which would move forward from the quantum mechanics that we know today.
Can I ask a little follow-on to that? How would your twistor theory, handle that kind of entanglement and breaking of entanglements?
Well, I'm not making any real claims for twistor theory here. All I would say is that it has quite a different perspective on locality. In twistor theory, one has non-local objects being described locally and local objects described non-locally. And there's a certain type of mathematics which is fundamentally local, non-local, which is a sort of complex holomorphic sheaf cohomology. Let me not bother what that's all about. But the thing is, it is fundamentally non-local. I can't say it answers the questions. It just has a framework for talking about non-local things, which seems to me to be moderately promising. But you certainly need something new. It shouldn't be just a description of the quantum mechanics that we know from ordinary theory. It's got to introduce new ideas. And at the moment, it hasn't got that far. That's all I can say.
Let's see, one last question over here.
Just a quick question. Does OR, gravitational OR, apply to massless particles, like the photons themselves?
Yes. Well, it would. The trouble is that it's hard to get a stationary object, you see. As I've described it, the only thing I know how to talk about were superpositions of two states, each of which is stationary. And if you're talking about photons, well, they have this habit of zipping along at the speed of light, and they're not very stationary. But you might be able to consider families of them which behave in some way like that. They certainly would be subject to it, but the trouble is they don't hang along very long and hang around very long, and so they're not very convenient objects to describe this. But sure, the idea is that it's a universal procedure and that it should apply equally to photons as to massive particles. It's just hard to think of situations in which the superpositions would be of the kind that these considerations are relevant for.
Well, a reminder that the last lecture in the series will be on Wednesday at 4:30 in Makosh 10. Let us thank Sir Roger once more.